Next, we move on to homogeneity of physical equations. An equation is homogeneous when each term in the equation has the same base unit. All valid physical equations must be homogeneous. In the example below, you have two valid physical equations, V equals to U plus AT, change in GPE equals to change in KE plus work done against friction. Now, the first equation that you see here is actually your kinematic equation that you will learn in the later chapters. It tells you the motion of an object that is moving under constant acceleration. V here stands for final velocity. U here stands for initial velocity. A stands for acceleration, whereas T stands for time. For the second equation that you have here is the energy changes that occur when an object is falling under the influence of gravity. As the object is losing height, it will lose GPE. But at the same time, because it's accelerating under gravity, it will speed up, so it has increase in kinetic energy. As it falls down, it encounters air resistance, so there's also work done against friction. This is something you will also learn in the later chapters, but for the time being, we are only concerned with the units of these given equations. Now, if we were to look at the first equation given here, when we want to analyze the homogeneity of the equation, we will need to analyze the units one by one, starting from one side. So we start off on the left-hand side first. The units of V, which is velocity, will be meter per second. And then we move on to the right-hand side. The units of U, which is also velocity again, would be meter per second. Now the units of AT, the units of acceleration times time, will be meter per second squared multiplied with second, giving you meter per second. Now you will see that each of the terms in the equation have the same units. The units on the left-hand side is the same as the units on the right-hand side, so the equation is homogeneous. Now we move to the second equation. Change in GPE can be expressed as mg delta h. Change in KE can be expressed as half mv squared, whereas work done against friction can be expressed as force times distance. Now, if we try to analyze the units starting from the left-hand side of the equation, the units of mg delta h would be kg times meter per second squared times with meter, giving you kg meter squared per second squared. Now, G is gravitational acceleration. It has the same unit as acceleration. Now we move on to the right-hand side of the equation. When you want to analyze the units for half mv squared, you know that mass has unit of kg, velocity has unit of meter per second squared, but how about the half here? Now, during your analysis, you will need to ignore half because this is a number, so it does not have any units. So this is ignored because it does not have units. So we proceed with the analysis. This one will be kg multiplied with meter per second. Remember to square the term, so you get kg meter square per second squared. Now, if we go to the last term, the units of force times distance would be kg meter per second squared multiplied with meter, giving me kg meter squared per second squared. So now, if you look at each of the terms again, each of the terms have the same units. So the equation is considered to be homogeneous. Now, it's important to note that not all homogeneous equations will be valid physical equations. For example, if you look back at the original equation, V equals to U plus AT, this is known to be a valid physical equation. What if when you try to recall the equation, you made a mistake in recalling it, and you accidentally added 3 and 5 into the equation. Now, this equation would not be a valid equation, but if you were to try the analysis for the units as before, you will notice that your analysis will end up looking like this, because you're analyzing the same terms again. The conclusion that you then get from there is that the equation is actually homogeneous, but in this case, it is a non-valid physical equation.